Okay, so for today, again, 5.2, this is the second section of concept 10. We're gonna have our test tomorrow. We'll start concept 11 on Wednesday, and then we'll continue that on for the rest of the week. This little warm-up, write a polynomial function to model each n behavior. To model, it's supposed to say model each n behavior. So if I have n behavior that is up and up, what's an example of a function that I could have that will model that will end up being up and up? Emma? X squared, correct. Okay. Any even exponent, it could be x to the fourth, x to the 8th, x to the 716th, as long as my coefficient is positive, and I have an even exponent, it will take on that n behavior of up and up. Then what about down and down? What's an example of a function that would be down and down? If x squared was up and up, what's it going to look like? Be another one. Ben. It wouldn't be an x cubed because we went down and down. Correct. We could have negative x squared. We could have negative x to the fourth. The important thing to get it going down is a negative. And then with them both going in the same direction, it has to be an even exponent. Okay? What about down, up? If I have n behavior where I look at it on the left, it's pointing down, and on the right, it's pointing up in s. X cubed. So a positive coefficient and any any odd exponent. So x to the 7th would work. X to the 13th would work. X to the 1st would even work. If I just said y equals x to the 1st, we know that's a line going right through the origin. There's no curves to this line, so it's pointing down on the left and up on the right. All right. What's that? It's frozen. Okay. There we go. And then up, down would be the opposite. And so I could say a negative x cubed, or I could just say a negative x, because y equaling a negative x is going the other direction. And so that would be up on the left, down on the right. So we're going to need to understand this n behavior for today's section, because this is going to be a small part of what we're doing. Okay, we need to know n behavior based on the degree of the polynomial, what's happening. And now today we're going to look closer at the actual zeros of the function and what's happening. Okay, so two forms of polynomials that we've talked about. Okay, we have standard form, and we also have factored form. Okay, so this is kind of a review. You don't need to necessarily write this slide down word for word, because this is stuff we've talked about before. Standard form of a polynomial, we know would be like 3x squared plus 3x plus 3 or something. That would be standard form of a polynomial, meaning that my exponents are decreasing. So there's really a 1 here, even though it's not written. And there's x to the 0, even though that's not written, because anything raised to the 0 power is 1. So standard form of a polynomial, I mean, we do this almost instinctively anyway, because we've been doing it enough, that we always write it with descending exponents. If we're given a problem and they give it to us out of order, the first thing we have to do is put it in order. So my largest exponent's on the left, and then I descend from there. Factored form. So factored form gets us back to this stuff with parentheses. So we could have like x plus 2, x minus 7 or something. That is a polynomial, but it's simply in factored form. Okay. I have on here, why do we like factored form? Because in factored form, if they told me, well, I want this to equal 0, I know the only time it's going to equal 0 is x is a negative 2 and x is a positive 7. So if I have it in factored form, I know the zeros of my functions, and the zeros simply mean where it's going to cross the x-axis. So we've talked about n behavior, kind of filling in from Friday. And now we can identify zeros of our polynomial. And now we're going to start to look specifically at what's happening at those zeros. Okay? Some additional terminology. We've talked about zeros over and over and over. You're going to start to hear me call those roots as well. So roots of a polynomial means the same thing as the zeros of the polynomial. It just simply means where it's crossing the x-axis at. Okay, and if it's set up as an equation equal to 0, the only way my output, my y value, be 0 is if I'm right on the x-axis. All right, let's just do a quick review of factoring. So if I want to write the polynomial in factored form, so let's just look on the one on the left. X cubed minus 2x squared minus 15x. I want to factor that, again, to get it into some parentheses, and I could have multiple parentheses, okay, but it's getting into that factored form where I've broken it down as far as possible. The one on the left is an x cubed. Chapter 4, we spent all that time factoring quadratics. Well, this is a cubic. We haven't really done anything with factoring cubics, but we can take what we know from factoring and still apply it. So what's the first thing that comes to your mind whenever you look at something to factor? What should you look for first? And as the greatest common factor. Okay? Always look, do I have a greatest common factor? Can I make this easier to factor? So this one I have x cubed minus 2x squared minus 15x. What would be my greatest common factor of this? Just x. That's as far as that's. I can't take a number out. The first term has 3 x's, the second term has 2 x's, the third term has 1 x. So I could factor an x out. So x times x squared would give me back to my equivalent x cubed minus 2x minus 15. So my greatest common factor in this one was just x, which I brought out. Now I have a quadratic in my parentheses that I can factor. So I'm trying to come up with two numbers that multiply to get negative 15, that to be a negative 2. All right. Negative 5 and a positive 3. Because my coefficient in my parentheses on x squared is 1, I can immediately jump to say x minus 5 and x plus 3. But do not forget about this x all the way here on the left that's going to come along for the ride. So x times x minus 5 times x plus 3. And there's no solving or anything. We're just practicing factoring on this. Okay. The one here on the right, 2x cubed plus 6x squared minus Tomas. Nope, because so you're wondering where this x squared went? So that's made up of these two x's in the parentheses. So here's so x cubed, here's my 3 x's. So if I were to multiply, I would still get 3 x's. Yep, good question though. Okay, the one on the right, 2x cubed plus 6x squared minus 8x. What would my greatest common factor of that be? 2x, okay, because 2 is in a number that I could factor from every single coefficient, and I could also take out an x. So again, I'm trying to rebuild, and so I'm going to have 2x times x squared is equivalent to x cubed, plus 3x, because 2x times 3x is 6x squared, minus 4. All right, so now I have a quadratic. Two numbers to multiply to get negative 4 that add up to be 3. Ben? 4 and negative 1. And because my coefficient on x squared was 1, I can immediately jump to say x plus 4, x minus 1, and I'm done. Again, this was just kind of a review on factoring because we need to be able to do end behavior stuff. We need to be able to do factoring, identify zeros. All that's going to come together here in a minute. Okay, so we got to be comfortable with our factoring. All right, so let's put one of these together. If I had this function, y equals x minus 1 times x plus 4, what are the zeros of this function going to be? Where do I know this will cross? Ben, what do you say? Okay, so if x is 1 and x is negative 4, that is where it's going to cross the x-axis at. So I already know if my function is in factored form, I know what my zeros will be. And in this case, they're going to be 1 and negative 4. And that simply means that's exactly where it's going to cross on my x-axis. What about end behavior? End behavior comes when our polynomial is in standard form. We get it in standard form. We look at the coefficient, if it's positive or negative, and we look at the exponent, if the exponent is even or odd. So for this one, to get it into standard form, I need to use the distributive property in FOIL. So x minus 1 times x plus 4, that would be x squared plus 4x minus x minus 4. And so I'm going to have x squared plus 3x minus 4. So x squared, what is my end behavior on a positive x squared? Grace. Up and up. Okay, so I can use that, and I know here at negative 4 it's going to be going up, and at 1 it's going to be going up. So I can fill that in a little bit, because I know my end behavior, it's got to go up and up from those 2 points. And if those are my only 2 points, and it was going up and up, this had to have dropped down, and my graph would look like that. Okay, I'm not so much worried about the vertex. I'm just asking for you to sketch it. I'm looking that the zeros are correct and that the end behavior is correct. So I know this is just a quick sketch. We could do our vertex formula, negative b over 2a, find out exactly where the vertex is at. We could find some more points. But I'm just looking for a quick sketch using the zeros and using the end behavior to fill in what shape this will take. Okay. Let's do another one. What are my zeros for this function? Where will this one cross the x-axis at? Ellie, what do you say? Not positive, because we want all of this to equal 0. So let's solve it. So you're on the right track. So 2x minus 7 equals 0. How do we solve that for x? So we could add 7 to each side. So we just end up with 2x equals 7. And so if we divide by 2, x would equal 7/2. So we have to solve each set of parentheses, figure out how we make that parenthesis equal 0. And so we have x is a negative 5. X is also a 7/2. And then here, x could be 0. So we have 3 zeros for this one. If x is 0, the whole thing goes to 0. If x is negative 5, the whole thing goes to 0. If x is a positive 7/2, the entire thing goes to 0. What is 7/2 as a decimal? Ari, come on. What's 7/2 as a decimal? 7 divided by 2. 3.5. Okay, so I only actually do it as a decimal because it's a little bit easier to graph as a decimal. So 3.5 0, and also here at -5. So I know these three are my zeros. It is going to cross the x-axis at all three of these locations. End behavior now. End behavior on this one, I can work this all out. Well, first off, I'm going to FOIL. Let's just FOIL the two sets of parentheses. So if I FOIL this, I'm going to have 2x squared minus 7x plus 10x minus 35. And so I have 2x squared plus 3x minus 35. But do not forget about that x that we also have going on. So when I FOIL my two parentheses together, I got 2x squared plus 3x minus 35. But I still have one more step because I have an x on the outside that I have to multiply in. And so this is the distributive property. I'm going to distribute each one of these in, or this x into each term. And so I have 2x cubed now, plus 3x squared minus 35x. Two x cubed. Using ups and downs and ups and downs, what's my end behavior of 2x cubed? Down, up. Okay, so I know here at -5, it's going to be going down after -5, and it's going to be going up after 3.5. That's how that end behavior comes into play, down and then up. So the only way to follow, if I'm going below the x-axis at -5 and above the x-axis at 3.5, it would have had to have looked something like that. Again, I'm not too worried on how high and low your peaks and valleys are, but I want to see that shape and that your line is crossing through the zeros, because it's going to cross through those zeros. We're just kind of sketching what it looks like, but it's going to take this curved shape crossing exactly through these zeros, going up after it gets to 3.5, going down when it's prior to -5. All right, let's just do a little practice here. Let's work in our standard form again. So write a polynomial function in standard form with these zeros. So I'm telling you now, we have some function going on that we're going to create, but it has zeros. It's crossing the x-axis at 5, 0, and -2. So if I know my zeros are at 5, 7, and -2, or I'm sorry, 5, 0, and -2, I need to create a function, and let's start off in factored form, because if I know 5 is a solution, what is one of my factors in my parentheses going to be? Not 5. I think I heard something. Specifically -5, what do you mean? X minus 5. So if I had a parenthesis that said x minus 5, I know at 5 it's a 0. What about -2? Let's skip the 0 first. What's the -2? What's that going to look like? X plus 2. How do we get one that equals 0 in S? Yeah, just a plain X that's not inside any sort of parentheses. And then you can do a quick check. Well, I have X times X minus 5 times X plus 2. Yep, my zeros of that would be 0, +5, and -2. But I want it to be in standard form. Remember, standard form is with descending exponents. It is not, this is factored form. I can take zeros and put it into factored form real quick. But now I need to write it in standard form, and so I'm going to do some foiling. So x minus 5 times x plus 2, I can multiply those together. That would be x squared plus 2x minus 5x minus 10. So that's x squared minus 3x minus 10. So I'm getting closer. My last step, I still have to multiply that x in to every single term. And so I'm going to have x cubed minus 3x squared minus 10x would be my function in standard form that has zeros at 5, 0, and -2. So you'll notice a lot of these problems we're going forwards with them, we're going backwards with them, we're starting in the middle of some of them, that we got to be comfortable moving all around within the problem based on the information they give us. So in this one, they gave us the zeros, we got to work backwards and figure out what the function is. Okay. Next thing we're going to talk about are what are called multiplicities. So this is something new, something that you haven't seen before, but this is something that you will be tested on tomorrow, so I want you to pay close attention on these. Multiplicities now will tell us behavior exactly at the zeros. So we've talked about end behavior, we've talked about finding the zeros. Now we can figure out exactly what's happening at the zeros. Okay, so multiplicity is simply just how many times multiply. For example, if I had x minus 3 squared, we know that just means x minus 3 times x minus 3. That squared is just saying that there's essentially 2 of them. So we say this has a multiplicity of 2, because it's x minus 3 times x minus 3. There's 2 sets of parentheses going on, but we simply write it as x minus 3 squared. Multiplicities are repeated zeros. Again, x minus 3, we could figure out the zero of that would be a positive 3. Okay, so there would be 2 positive 3's going on, essentially. Those are my zeros. But the biggest thing I want you to take away from this, the multiplicities affect the behavior at the x-axis on the graph. So when we're graphing our line, specifically at those zeros, we can determine what's happening based on multiplicities. So we'll start off with a multiplicity of 1. If we have a multiplicity of 1, that simply means that the graph goes straight through our x-axis. Okay, and so it'd look like if we had just a simple one, we'll say x plus 1, and I'm going to raise to the first power just so we recognize it's a multiplicity of 1. There's this 1 going on. If I were to graph x plus 1, it's going to cross the y-axis at 1. That's my y-intercept. And then it's just going to go straight through my x-axis. All right, there's no curving or anything going on. It's simply going to go straight through because I know x plus 1 has a 0 of -1. That's where it's crossing the x-axis there at -1. So specifically at -1, it's just slicing right through my x-axis. There's nothing crazy going on. It's just going straight through. So when we say a multiplicity of 1, it's just going straight through. A multiplicity of 2. Our graph will bounce off the x-axis. So for example, a multiplicity of 2, let's say we have x plus 3 squared. All right, x plus 3 squared. Let's just do it as x squared. That'll be easier. Let's just say x squared. And that is a multiplicity of 2. It's x times x, essentially. We know that that's a parabola that looks like the U shape with a vertex at the origin. So when I say bounces off, it's bouncing off the x-axis. It is not going through the x-axis. It's just bouncing off. So a multiplicity of 2 will cause a bounce. And my other one's already up there. A multiplicity of 3, it will snake through. So if we had x cubed we know looks like this. So it kind of curves through the origin. It's not straight through like our linear or multiplicity of 1. It's not just slicing through it. It has some curving as it's going through the x-axis. So these are the 3 we're going to focus on in terms of multiplicities. Multiplicity of 1, it's going to go straight through. A multiplicity of 2, it's going to bounce. And a multiplicity of 3, it will curve or snake through the x-axis. So this is specific behavior at the zeros of our function. All right, so let's do one nice example here of how we can graph with multiplicities. So if I had this function, x to the 4th minus 2x cubed minus 8x squared. The first question they give me, what are the zeros of the polynomial? So how do I find the zeros when it's in standard form? Got to get it into factored form first. Okay, so let's do some factoring. What is the greatest common factor for x to the 4th minus 2x cubed minus 8x squared? Can I factor out a number, a coefficient number? Nope. How many x's can I factor out? 2. So I could say, well, x squared times x squared minus 2x minus 8. Okay, and now I can factor now my quadratic in my parentheses. X squared minus 2x minus 8. 2 numbers I can multiply to get negative 8 that add up to be a negative 2. Negative 4, positive 2. And so I still have this x squared on the outside, x minus 4, x plus 2. So this is my function here. It's still the same, but now I'm in factored form. So from here now, I can identify my zeros are what? An S. 0, 4, and a negative 2. Okay. What about end behavior? This is going to be up, down, down, up, 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 or down, down. An S. It's not down, up. All right. Up and up. And we can look up here at standard form, x to the 4th. It's an even exponent and a positive coefficient. And so this one's going to be up and up. Okay. Multiplicities. Okay, so these next two kind of go together. So the multiplicities, I have that x squared. And so that tells me there's going to be a bounce at x equaling 0. Okay, because 0 is the 0 of x squared. X squared has a multiplicity of 2, and so I know there will be a bounce at 0. And then I have x minus 4. This has a multiplicity of 1, because really there's a 1 on the exponent that we went right. And so I know this is going to mean straight through straight through at x equaling 4. Because x minus 4 had a multiplicity of 1. Multiplicity of 1 tells me it's straight through. So specifically at 4, I know my graph is going to go straight through. And then last one, x plus 2. This has a multiplicity of 1. So again, this one is straight through. Straight through at x equals a negative 2. So let's put all this information together and just make a quick sketch. Well, I know my zeros are going to be here at negative 2, at 0, and at 4. I know my end behavior is up and up. And now I know specific behavior based on the multiplicities at every single 0. All right, at 4, it's going straight through. So that cut right through there at 4. At 0, it's bouncing. So it's going to go up, touch the x-axis, and bounce right back down. Specifically at 0. It's going to go up, touch it, and bounce right down. It's not going to cross the x-axis at all. And then at negative 2, it's going straight through. So this has to curve back up. And it'll go straight through negative 2 on my x-axis. So this is how my graph will look of x to the 4th minus 2x cubed minus 8x squared. Okay? I got a couple more, but I'd rather you get started on the assignment. That way you can ask me questions on it. Okay, but that idea of multiplicities, you're going to have to do a few of those. So for the remainder of class, let's work on page 293. Here are the problems up here as well. 9, 10, 12, 13 through 18 odds, 27 through 34 odds. It equates to about 10 problems right there. But then I also have an IXL in the Algebra 2 tab that I want you to be working on. Okay, have these done, ready to go. Tomorrow when we start class, we'll probably take the first 10, maybe even 15 minutes. I'll do at least one multiplicity problem that I'll present. And if you have questions on any of these homework problems, that's the time to ask them, because you will be tested on this multiplicity stuff tomorrow. So come with questions on it so that you're ready to go.